Welcome to Signals and Systems course. In this class, we will be learning about periodicity. Periodicity of both continuous signals as well as discrete signals. Periodicity concept is the most important concept in the field of signals and systems, and this particular concept is rigorously used in developing the Fourier series. Fourier series anyway we will see later, but let us first understand what is periodicity or what are periodic signals in the concept of continuous as well as in the discrete signals. Let us first understand in the continuous time domain. So any signal that satisfies x of t equals to x of t plus or minus kt is said to be periodic signal. Okay, so what is t? T is what we call the time period of the signal, okay, and k will take integer values. Integer values, I mean to say 1, 2, 3, 4 and so on. Okay, so any signal that satisfies this particular equation is said to be periodic signal. Now, there are some basic properties of the periodic signal. So, what are those properties and how do we understand these properties with respect to a particular signal? Let us understand. There are many examples that I will be showing in this particular concept. The first and most important thing in periodic signals is that all periodic signals always exist from minus infinity to plus infinity. That is the first check that always we have to see. So they exist from minus infinity to plus infinity. If any signal that does not exist between minus infinity to plus infinity or exist in a particular interval or in a particular point to point, some finite point to finite point, then they are not periodic signals. Why they are not periodic signals? That we will see anyway. And the second property is that this t. So there are some points that we have to understand about this particular t. That means t can be. So there are some properties of this particular t. Let us also understand them. So integer multiples. Okay, integer multiples in the sense t can take 1, 2, 3, 4, 10, 11, 30, 50, any number, any integer a t can take. And the second point is t can also be rational. What do you mean by rational? What do you mean by rational? A rational number in the sense it must have m by n format and both m and n are integers and n should not be equal to 0. That means denominator should not be equal to 0. So therefore it can be something like 2 by 3, 4 by 5, okay, 10 by 11, anything. Okay, that means that while you are solving the problems to find out the periodicity, before you conclude the answer, you must see that whether they are following these 4 properties or not. If the signal is not following, I will be completing the next 2, but if the signal is not following these 4 properties, we should not, or we should conclude that it's not a periodic signal. Okay. Now the third one is, point, t can also be integer multiples of pi. Integer multiples of pi. Okay, so that means what? So that means t equals to pi, 2 pi, 3 pi, 4 pi, 10 pi, integer multiples, right? So now you can see, so what is the multiple of pi here? 1, 2, 3, like that. Okay, it can also be 10 pi, 11 pi, 20 pi, anything. Okay, and the last property, the fourth property is that rational multiples of pi. Rational multiple of pi. Rational multiple of pi. So what do you mean by rational multiple of pi here again? So that means t equals to pi by 2, okay, some 3 pi by 4 and so on. Is it not? So that means again you can see that pi coefficient is 1 by 2 and here pi coefficient is 3 by 4 and so on. So therefore these 4 properties, so the t must be any one of these 4. Okay, so they exist from minus infinity to plus infinity and they should satisfy any one of these 4. Apart from this, if t takes any value, suppose t equals to root 2 or t equals to root 3 by 2 or t equals to something like pi square, they are not allowed. So these are the certain things that we have to really understand before you understand about the time period. Okay. Now, let us draw some basic periodic signals. Okay. So, what is the point that I said? It must be from minus infinity to plus infinity. So therefore, this is minus infinity, and whereas this point is plus infinity. So now you look at the signal. Okay. Now, this is a typical periodic signal. So this can be minus t by 2, and this is t by 2. This point is A, and I will call this as x of t. So minus t by 2 to t by 2. So obviously from this point to this point is t, okay, because that's a duration. So what is the minimum cycle that is getting repeated? Okay, or what is the smallest part of the original signal that gets repeated? Now if you take this particular triangular signal, the triangular that gets repeated, right? So therefore the width of this particular one is t. So that's what you call it as a time period. Okay, now so this is t by 2. So therefore what is this width now? So this width is also t, is it not? That's also t. So therefore, what would be this point? This point is nothing but t by 2 plus t, that's equals to 3t by 2. So this point is 3t by 2. So that's how you can also understand the time points. Let's draw one more signal on this. We can draw as many signals as possible. Okay, so this is 0. Oh, sorry, this point is t by 2 and this is t, and this happens to be a, then obviously this is going to be minus a. So this is, again, you can call it as x of t or x1 of t, whatever the signal. So this is also a kind of a periodic signal wherein you have this signal from minus t by 2 to plus t by 2, or you can also consider this part. So you see the shaded portion, that shaded portion is always getting repeated. So that is also an example for a periodic signal. I'll be drawing some signal here. Let's say that there is some signal which is something like this. This is minus infinity and this is plus infinity. Let us call this as something like y of t. This signal also exists from minus t by 2 to plus t by 2. But I could not see any a portion of this particular signal that gets repeated. I don't have any portion here, because if I consider from this point to this point, if I say like this, as I do it for the earlier two signals, but that's not the point. Again, it is getting repeated because the portion, the shape that I have here is not same as the portion that I have here. So this is an example for a non-periodic signal. This is an example for a non-periodic signal. Hope you understood what are the periodic signals. So the best way of understanding a periodic signal, which we have seen many times in physics and fundamentals of mathematics, is a simple sinusoidal signal, is it not? A sinusoidal signal. So wherein this is going to be amplitude A and this point is 0, this point is t by 2 and this point is t. There's a simple example for a sinusoidal signal. Sinusoidal is also mean cosine. Okay, so both sine and cos signals both are called sinusoidal. That's actually cos. We call it as a cos, but what is this? It is cosine, is it not? So both are in fact sinusoidal signals. Both are having the same properties, but there is a phase shift of 90 degrees between cos and cosine. That we will see. We can understand that point later. Now, let us understand some numerical examples on this. Like, given a particular signal, how do we calculate the time period and what is the formula for the time period? To do that, let us look at this signal. X of t equals to e power j omega t. Okay. At this moment, I am not plotting the signal. I'll plot the signal in Fourier series. Okay, but let us understand that this is a complex signal, because if I expand this, I would get cos omega t plus j sin omega t. So which is a typical complex signal, and you need to plot the signal on the complex plane, not on the just x-axis and y-axis, because plotting complex signals is slightly different than the plotting the ordinary signal. So therefore, I will plot this in the Fourier series, or you can also look at the Fourier series lecture where you will understand how to plot these kind of the signals. But let us use this particular signal now and then understand how to calculate the time period. Okay, so what did I say? That any signal that satisfies x of t plus or minus kt, is it not? So at this moment, let us assume that k equals to 1. Why k equals to 1? That you'll understand at the end of this derivation. Okay. So now then what is x of t plus capital T e power j omega t plus capital T? Is it not? I just replaced t with capital T in the equation. According to the periodicity concept, x of t must be equal to x of t plus kt, which means that x of t equals to x of t plus capital T. Is it not? Now, let us substitute both here. So this is e power j omega t. This is e power j omega t. Okay. So I can separate this. Is it not? E power j omega t. I can do like this. But when bases are same, powers are added. I can cancel these two things, right? Okay. So now what do I get? E power j omega t equals to 1. All right. So now let us expand on the left hand side. So how do I expand on the left hand side? Cos omega t plus j sine omega t, which is equals to 1. You cannot compare two complex numbers. Okay, so let us don't say that a plus jb versus c plus jd. You cannot really compare, but you can always compare the real parts as well as their imaginary parts. So keeping that point in mind, because if you look at on the right hand side, it is 1 plus j0. I can write down like that. Is it not? 1 plus j0. So therefore, equating the real parts as well as on the imaginary parts. But if I equate the imaginary parts, I don't get anything because cos omega t equal to 0, and from that I cannot conclude any point. So therefore, now let us take the real parts of this particular equation. So what is that? Cos omega t equals to 1. Okay. So now on the right hand side, let us use the little bit trigonometry to understand this better. Not a complex trigonometry, but small things. Okay. So that is equals to, is it not cos 2 pi k, right? And k supposed to be 0, 1, 2, 3, and so on. All right. So I can say that point. Now you can drop cos both sides. So therefore, omega t equals to, I will say that 2 pi k, and where is k equal to 0, 1, 2, 3, and so on. Okay. But k is not equal to 0. If I make k equal to 0, what do I get? If I make k equal to 0, what is the equation that we will land on? So I would get omega t equal to 0. Okay. So either omega equal to 0 or t equal to 0. T is not equal to 0, that we know, because we are trying to find out the time period, and you cannot say t equal to 0. Okay, even I make capital T equals to 0, time period equal to 0, what do I get? I get x of t equal to x of t, which is always right. Okay, there is no point in contradicting that. So therefore, t is not equal to 0. Then you land on omega equal to 0. If I make omega equal to 0, actually there is no signal. You get equals to e power 0 equals to 1. Is it not? Then you get x of t equal to 1. X of t equal to 1 is a DC signal. Okay. So DC signals normally do not have the time periods. So therefore, omega should not be equal to 0. T should not be equal to 0. So that means that on the left hand side component can never be equal to 0. So when omega is not equal to 0, t not equal to 0, then k equal to 0 is not a valid point. Okay. But that k equal to 0 always gives me DC component. Okay. K equal to 0 gives me DC component. What is that I'll just let you know after this derivation. Now let us substitute k equals to 1. Okay. So because I am substituting a particular value of k, so therefore I will be taking a particular value of omega. So therefore I will assume that omega equals to omega naught. Okay. So that gives me omega naught t equals to 2 pi, which implies t equals to 2 pi by omega naught. This is the derivation of the time period. Actually, this formula we know, because even in the physics and basics of periodic signals, whenever you are doing this, normally this formula we will take it. But there is a little derivation behind this, because I wanted to emphasize on something called harmonics here. Okay, that's the reason I've derived this, and this derivation is also very important because this is the point where you will understand the concept of the DC component also. Now, when k equals to 1, when k equals to 1, this is what you call fundamental frequency. Fundamental frequency. Okay. When k equals to 1, that's what you call it as a fundamental frequency. And because it is 1, so therefore we will also call this as first harmonic. First harmonic frequency when k equals to 1. Then what happens at k equals to 2? Okay, k equals to 2, it is called second harmonic frequency. Second harmonic frequency. Okay, and k equals to 3, third harmonic, k equals to 4, fourth harmonic, fifth harmonic, sixth harmonic, and finally you can also understand something called nth harmonic. Nth harmonic frequency. Okay, right? So normally this fundamental frequency we'll call it as f naught. Okay, and second harmonic frequency we call it as 2f naught, and nth harmonic frequency we will call it as, it's going to be n into f naught. Okay, so that's how you can interpret that. However, what are harmonics now? What do you understand by harmonics now? What do you understand by harmonics? Harmonics are integer multiples of fundamental frequency. Fundamental frequency. Integer multiples of fundamental frequency. That means f naught, f naught. So what is f naught coefficient? 1. It's actually 1 into f naught. So therefore, this is called, of course, fundamental frequency. There is no doubt. Okay. But however, this is also called first harmonic. That is what I said just now. First harmonic. And 2f naught is called second harmonic frequency, right? And 3f naught, integer multiples, that's what I said, third harmonic frequency, and so on. And nf naught supposed to be nth harmonic frequency. Okay, that's the point. So for all these category of the problems, we will be using the formula that we have derived in the last slide. Okay, so what is that formula? So what is that formula that we have derived? So T equals to 2 pi omega naught. Okay, so this is the main formula, and based on this we'll be solving the problems. Now let us once again understand this. So what is the formula now? T equals to 2 pi by omega naught. Okay, so we will do that, and that is also equals to 2 pi by 2 pi f naught, because we know that omega equals to 2 pi f, is it not? So I can cancel these two so that I get 1 by f naught. This formula also we know, because this formula we have studied many times. T equals to 1 by f naught also we have studied many times. So therefore, this is the main formula to understand the time period, and of course the derived formula could be T equals to 1 by f naught. Let us understand one basic signal here. Okay, suppose I have something called x of t equals to a sine omega naught t plus theta. Okay, so to plot a sinusoidal signal, we require three values. Okay, one is we require amplitude, we require omega naught, we also require theta. Omega naught and time period both are similar. Similar, I mean to say that they are related to each other. Okay, so therefore, if I don't give amplitude, I can plot n number of sinusoidal signals with varying amplitude, that you can really understand it. What I mean to say is that now let us look at this. This is one sinusoidal signal, and varying A is going to be something like this. So this signal, the first signal and second signal are varying with respect to the amplitude. Okay, because both are starting at the same point, so therefore their phase is same. Okay, their phase is same. I'll give you one more example. Suppose one signal is like this, all right, the second signal is like this. Okay, now if you look at the difference, this is what is going to be theta. Okay, they have the different phases, but indeed this is something like a time shifting. That is what actually you can really interpret, but I'll let you know why this is also called phase, but later, not now. Okay, so coming back to this point, so I have two sinusoidal signals with same amplitude but different in phase. Same phase but different in amplitudes. I can also plot some other signals with um, same amplitude but different in time periods. You look at this, these two signals are having different time periods, because the time period of this signal is from this point to this point, and the second signal is this point to the other point. Okay, so there is a difference in the time period. So therefore, conclusion is, what I wanted to say, that this amplitude and phase will not affect the time period. Okay, I can have two different amplitudes, same time period, two different phases, same time period. Okay, because time period formula consists of only omega naught. Time period formula does not consist A and theta. So you observe this, time period formula does not consist A and theta. So time period formula consists only omega naught. Because it consists only omega naught, so therefore only the angular frequency, that's what we call it, the angular frequency depends on the time period. Okay, now let's solve some problems, some numerical problems on this. X of t equals to 4 sine 2t. So what is the time period of this signal? Okay, so immediately you can compare this signal x of t equals to, okay, what is the formula that we have derived? A sine omega naught t plus theta. So if I compare these two, what is omega naught value from this? Omega naught value equals to 2, is it not? Because t coefficient, so t coefficient is 2. Omega naught equals to 2. So what is the formula that we have? Time period equals to 2 pi by omega naught, that is 2 pi by 2, which is nothing but pi. Therefore, t equals to pi. Simple problem. Okay. Now, x of t equals to, let us say, 4 cos 2t. 4 cos 2t. Now, what is the formula for this? Same formula. Formula will not be changed. So, whether it is a sine or cos, that really doesn't matter, because that's what I said. How do I understand the sine and cos? Sine and cos are differ by phase. That's it. So, therefore, I can still write this cos in terms of sine by introducing 90 degrees phase shift. But just now we have seen that this phase and amplitude do not affect the time period. So therefore, there is no need to again write the cos 2t in terms of sin 2t and solve the problem. Not required. So therefore, time period equals to, again 2 pi by 2, that is equals to pi. You have the same time period. Okay. Now, cos square 2t. Let us see this. You cannot directly apply this formula for this cos square 2t. You know why? Because if you can just recollect in today's class, the t equals to 2 pi by omega naught formula we have derived assuming that x of t equals to e power j omega t. Is it not? What is e power j omega t? What is e power j omega t? Cos omega t plus j sin omega t. You look at it, it is cos omega t, j sin omega t. It is not cos square omega t plus j square omega t. So therefore, this particular problem you cannot directly do using this. So what do? You apply transformations. We know transformations, right? Okay, cos 2 theta. So what is the formula that you know? Cos 2 theta equals to, you have many things there, cos square theta minus sin square theta, okay, or we have the cos square theta, which is nothing but 1 plus cos 2 theta by 2. Okay, I'm not going into deep of this trigonometry because that's a basic thing, right? So you apply that formula here. So then how do I write down that here? How do I write this in terms of cos 2 theta? Cos square 2t equals to 1 plus cos 4t divided by 2. Okay, that way I can write down using this formula. Now I can separate this 1 by 2 plus 1 by 2 cos 4t. Is it not? Okay, you can leave this 1 by 2. What is this 1 by 2? This 1 by 2 is DC component. Okay, that will not affect your time period. Okay, how? I'll explain in the next problem. Okay, but right now you can just consider this and you can apply the formula. So what is t here? T equals to 2 pi by 4. That gives me pi by 2. As simple as this. You can leave this amplitude because amplitude does not affect the time period, and this 4 you can take it, and 2 pi by 4, that is equals to pi by 2. But let us also focus on this, okay, DC component. I'll give you one example on this in the DC component. How do I plot these two signals? X of t equal to sine t and x of t equal to 1 plus sine t. How do we plot these two? Okay, so how do I plot x of t equal to sine t? We know this. Okay, so this is sine t graph. Okay, and 1 plus sine t, that's nothing but you have to add 1 to this. Whenever you add a DC component for any signal, that will be clamped. Okay, it will clamp either in the positive direction or in the negative direction. So therefore, depending on this particular signal, let us say that this is 1, then this is going to be minus 1. Now you add 1 to this. For every amplitude you add 1. So if I add 1 here, it's going to be 0. If I add 1 here, that's going to be 2. So therefore, your signal moves in the upward direction. Okay, so if you shift your signal on the right side, either on the left side, that's not normally you call it as a time shifting, because this is time axis. This is time axis. So that's what you call it as a time shifting. But if you move in the upward direction or in the downward direction, you can really do that. That's what you call it as a clamping. And there are some circuits that will do this clamping, which are called clampers. Okay, clampers and clippers. Clippers are normally sliced off. They slice your signals. That means that either this part or this part they remove it. They are called the slicers. So that the clip. Okay, and this is clamp. So clamp is like this. So therefore, your signal. So if we move the signal in the upward direction, that's how you see the signal. Okay. By just moving in the upward direction and downward direction, we do not lose time period. Okay, time period remains same. Even this signal exists from minus infinity to plus infinity. Even this signal also exists from minus infinity to plus infinity. Is it not? And also there is a small portion of time that gets repeated. And here also there is some portion of time that gets repeated. So therefore, if you just clamp your signal, the time period will not be lost. So therefore, still this is also a periodic signal. So that's what actually the concept of the DC component.